All right. Cool. Looks like we do have audio. Great. Okay. Couple of things up here. Here's our syllabus. I adjusted it over the weekend because odd is actually ahead of even day because of that whole, the first 3 days were only 45-minute days and all that stuff. So as far as the next kind of big thing that we have for us on even day, on the 14th, is our first quiz. As far as what does it cover, if you have your notes with you, it's the first page of your notes, and then on page 2, the lipids section. So I can flip this over for y'all watching the video. And I'm very excited. Keller got some new cameras. I don't know how they got them because cameras are out everywhere. Around early July, I went to Office Depot just to see what webcams they had. And I was like, hey, do you have this type of webcam? They're like, we have no webcams. And I'm like, none? And they're like, we actually have 0 webcams in stock. So anyway, I'm excited. Keller got us some new ones, so I'll use my new one. But then I'll also get to finally replace this one that's like 12 years old and junky. So very exciting day for me. Doesn't take a whole lot. So as far as our quiz, if you're in the even day class, it's on the 14th. If you were in the odd day class, I know I'm not talking to you guys, I'm talking to them. If you're in the odd day class, then it'd be like the 11th in theory. And it'll cover anything on the first page of your notes, and then the lipids section of page 2. So lipids is kind of like this little chunk here in the middle that says, you know, lipids. All right. And then our first test for you guys, you're my even class. Our first test is on September the 18th. So I'll always have this up here. It's on the Google Drive. You're always welcome to take a picture of it as well. So while that's up there, if you kind of put your camera up like this or your phone up like this, I kind of get out of the way if you wanted to take a picture or anything. And yeah, I think that's it. I don't think that this will change, so I think this should be pretty solid. All right, any questions before we get rolling? Cool. Anybody else need it? Okay, I'll give you a second. Audio's still working good. Okay. So we'll get rid of that. That's pre-AP. There you go. Have we got a chance to talk about a gecko foot yet? Okay. Depending on what you saw. So you were originally remote. Okay. Yeah. So you'll find that part of today is stuff you've learned, and then we'll get into parts. So you might be like 20 minutes ahead or something like that. Okay. Like the methamphetamine and...
The cells?
Mm-hmm.
Does that mean it's only about the 4 cells?
Yes. Yes. So you're actually like more than half a day ahead. So this will be kind of review-ish stuff for you. Okay. So on your notes, one of the things that I kind of do sometimes is, because we're just sort of like teaching and learning and stuff, I'll go back and make sure that I like didn't miss something. And if it's important, I'll go back and kind of cover that thing. So on your notes on the very front page under bonding, it has 1, 2, 3, and 4. 1 was covalent, 2 was ionic, 3 was hydrogen bonds. We talked a lot about hydrogen bonds with water. Number 4, van der Waals forces. So van der Waals forces explain gecko feet. Most students, I think you don't learn about van der Waals forces until like AP chemistry. So unless you've had AP chemistry, which most students haven't, then this will be pretty much brand new information. So you got a gecko, and a gecko can actually just walk around on like a plate of glass. Like there could be a gecko sticking to that window out there just like spying in on us. I told some of my classes, we had a house, my family and I had a house, and there was a window on the 2nd floor of the bathroom, and there was a gecko that would like hang out there, just like he was like a peeping Tom gecko or whatever. So you'd be getting out of the shower and there's this gecko that just kind of like staring at you or whatever. I was very offended. And so anyway, it was always surprising to me, like he had to be able to climb up the brick, and I'm like, all right, you know, I've seen Alex Honnold and dudes like that, so I can understand the brick, but like, how do you stay on like a surface or like, you know, plate glass or something like that? Well, van der Waals forces explains it. So another thing that I always give as an example with my students is if I was awesome, which I'm not, then I would run on like first day of school, I'd be like, welcome to biology, and I'd run and I'd like kick off the front wall and like do a flip. You ever seen that? Have you seen all the fails of people trying to do that and then it didn't quite work out? Yeah. So that's what would happen to me. So for just a second, when I run and I push on the wall, aren't I somehow, maybe bonding's not the right word, but aren't I like interacting with the wall enough to where like I'm sticking to it hard enough that like it actually supports all of my body weight plus the force of me pushing off the wall? Like, isn't that pretty impressive? So in physics, we just call that friction, right? Well, in chemistry, we call it van der Waals forces. So van der Waals forces explains friction also. So let me kind of show you what I mean. I like blew a vocal cord or something last week, and my voice still hasn't recovered. So I don't know what that means. It's probably bad. I don't understand like how rock singers like the dude in Disturbed or whatever, like I don't know how he can sing like that for like 5 nights on, 2 nights off, 5 nights on without destroying his voice. Okay, so van der Waals forces. Let's say that this is my shoe. And these are atoms on my shoe. These are like the electron clouds of the atoms. So the electrons are just kind of everywhere. And then this, use a different color. Different times a day, the students that are watching online prefer different sort of lighting. And here's the wall. So this is just some atom with an electron cloud. This is another atom off of my shoe. I've got tons of atoms on my shoe. I'm just putting in a whole bunch of negatives because these are negatively charged electrons. Okay, so here's what will happen. The electrons are just kind of like randomly on there, but whenever I shove my foot really, really close to the wall and these atoms get really, really close to these atoms, the electrons repel each other. And so one of them gets repelled first. So it's almost like if I'm on ice, seems like in physics everybody was always on ice skates or something, but if I'm on ice skates and the other person's on ice skates and we push off of each other, it looks like we both move, but technically one of us, if we had like a great, great camera, probably one of us actually moved first. We can't see it with the naked eye. It would look like we both move, especially if we weigh the same and everything else. We'd look like we both just move equally. But somebody actually started to move first, probably. So that's what happens with these electrons. These electrons get close to these electrons. Hey, come on in. Get close to these electrons. And, oh yeah, if you don't have a chair, you'll have to grab one from the back. We, a couple times a week, we stack the chairs so that the custodians can kind of clean the floors a little bit better. So when they get really close, these electrons like push these electrons away. So now it looks more like this. Now if I zoom in on this atom, all these electrons get pushed away over to this side. So if all the electrons are over here and not very many are over here, isn't this side kind of more negative and this side's kind of more positive? Temporarily, for just an instant. I don't even know how long, but super fast. So that side's kind of negative, that side's kind of positive. Well then, before these electrons move back, that attracts all the electrons over here. So then, on the wall, all of these electrons move over here because they're attracted to the positive. And this is how chemists explain it. To me, I'm like, wait, wouldn't before they get attracted, wouldn't these repel each other and everything else? And chemists are like, no. And I'm like, why? And they're like, shut up and accept it. And I'm like, okay. So now, for just a second, all the electrons are over here. So isn't this area like kind of negative? Don't negative and positive attract? So for just an instant, my shoe is sticking to the wall. Now, this is not a very strong interaction. In fact, out of the four, it's the weakest one. But how many atoms are in my shoe sole that's like touching the wall? Yeah, a lot. I mean, we start measuring number of molecules in moles, don't we? Like 6.02 times 10 to the 23rd. So yes, each interaction is really, really small. But if there are trillions of trillions, that adds up to pretty strong. So I give the example of tug of war. Tug of war against a bunch of first graders should be easy, unless there's like 50,000 of them. Then, even though each one's weak, 50,000 of them is strong. A penny a day is not much money, unless you got 1 trillion years. Then, all of a sudden, you're a multi-billionaire, right? So, these are called van der Waals forces. Okay, so for me, they don't stick for very long. I smear them on there, and enough molecules do this so that I can stick just long enough to flip. But for a gecko, their feet have folds on them. So let me go back to this picture. Oops, wrong camera again. There we go. So if I go back to this picture, a gecko foot has folds. And if you zoom in on those folds, they have folds. And if you zoom in on those folds, they have folds. And if you zoom in on those, they have hairs. And if you zoom in on the hairs, they have micro hairs and nano hairs. And then each hair on the end has a little spatula. So anytime something's folded in biology, what is the purpose of that? Almost always. Crap, I'm supposed to have kids zoomed in right now. Hang tight. Let me grab my Zoom info. Sorry about that. It felt like I had only set up like 20 things so far instead of 21. Poor students. Yeah, there they are. Virtual cam. Hey, y'all. Sorry about that. I could say it was technical difficulty, but I kind of just forgot about you. Hang on, let me get everybody buzzed in. That's good. Still have audio. That's good. Make sure there's nobody else in a waiting room somewhere. All right, you should be able to hear me in the chat if you can't. So, can you hear me? And sorry about that, we've been talking about gecko feet. Okay, there's another. There's another. All right. Isabella, if you can hear me, will you give me the thumbs up? Okay, cool. Thank you. Sorry about that. It felt like I was missing something, and it was Zoom. So, sorry about that. So, gecko feet. Gecko feet have a whole bunch of folds. Let me put a picture up here. So, on the gecko feet, they have tons of folds on their feet, and that's to increase surface area. So if I'm looking at the surface of my brain, why is it folded? To increase surface area, the outer part of my brain. If I look inside of a mitochondria, you might remember a mitochondria looks kind of bean-shaped, but then if you cut it open, it's all squiggly. That increases surface area. The alveoli in my lungs, little lung sacs, supposedly according to our anatomy and physiology textbook, if I take all the alveoli, little bitty lung sacs in my lungs, and I flatten them out to make sheets, supposedly that sheet is the size of a tennis court. So just having little bitty folds, all of a sudden my lungs that are only like this big, there and there, my heart's in the way, so my left lung's smaller, it's only got 2 lobes. My right one has 3 lobes. It's bigger because there's not, as much room taken up by heart or anything. So lungs that are this big actually have the surface area of more than the floor in this room. That's pretty significant. If I'm looking at gecko feet, they have all of these folds. And so now, whenever we're doing van der Waals forces, let me run through van der Waals forces again really quick. With van der Waals forces, what's happening is if a gecko was like walking up plate glass, the way that they stick is this weird like temporary interaction. Let me change back over my camera. There's this weird temporary interaction as they're moving up the wall. So if I've got something like this, here's my shoe, or here's their gecko foot, and the wall. I have a whole bunch of molecules of wall, and there's electrons in these electron clouds. That might be a little bit better. There are these electrons in these electron clouds all around, and the electrons are just sort of kind of evenly spaced. Same thing with the gecko foot. They're sort of evenly spaced. Like this all the way around. So how is it that a gecko can like walk on a plate of glass, like a glass wall or something like that? Well, in your notes, near the beginning, under bonding, it says like covalent bonds, ionic bonds, hydrogen bonds, and then number 4 is where it says van der Waals forces. Van der Waals forces is the explanation for why a gecko can walk on plate glass. So whenever he smears his foot against the wall, these electrons and these electrons start repelling each other. But when they do that, one of them kind of repels the other first. So let's say the foot wins, and all the electrons in the wall kind of shift over here to the right. These are just a bunch of minuses for electrons. So relatively speaking, that wall is kind of positive over here and negative over here. Well then, all the electrons in the foot actually get attracted to that positive. So these electrons shift to the right also. So now there's a crap ton of electrons over here. Eventually they're going to repel each other. But before they do, now the foot has kind of a positive and kind of a negative. So they're kind of attracted. And if I've got a gecko foot with folds upon folds upon folds upon folds, then now I've got enough of these interactions to where they can actually like walk up plate glass. Our hands, we've got a little bit of folds. It kind of acts like grip, we think, kind of like tread on tires, like a tire with tread can grip the road, a bald tire can't. So we think that the tread on our fingers, like our fingerprints, is for gripping stuff so that you can like palm a bottle of Oxivir. That type of thing. So we don't have as many folds though. So for us to hang onto a wall, we might have to have the surface area the size of, I have no idea, maybe Timber Creek or something like that before we could like walk on a wall. All we can do is temporarily like run, and if I slid my foot against the wall, I might be able to kind of kick off, you know, like parkour style or something like that. But I can't like walk all the way up a plate glass wall. So this interaction that's temporary is called van der Waals forces. They then bounce back out. But if I've got enough surface area, then there's enough of this going on and off to like hold me onto the wall. So they actually stay stuck to the wall. Even though each force is small, if I've got billions or trillions of them, then the overall effect is strong, which is kind of cool. So that's how gecko feet work. Good information to have. So more date information. I think I've given the analogy of like if you're ever bored on a date, science information is money. I mean, there's a lull in the conversation, gecko feet. If she doesn't like it, she's not good enough for you anyway. That's my theory. All right. We have not talked about scurvy yet in here, correct? Okay. So we'll talk about gecko feet, then scurvy, and then we get into lipids and saturated fats and unsaturated fats, which is really interesting. If you're on your notes on the first page, under the water section, out here near hydrogen bonds, it talks about scurvy just a little bit. Just happens to mention scurvy and hydrogen bonds. So scurvy is a really interesting application of hydrogen bonding. So here's a guy that I affectionately named Dale. He sort of looks like his name would be Dale. Plus, I don't currently have any students named Dale, so it seems like it's less insulting. So here's Dale. Dale's losing his teeth. He's kind of looking a little bit unhealthy in the eyes. His skin isn't doing so well. It says pale skin, and you're like, I don't know, Cotton, you've got pretty pale skin. But one of the problems with his skin is all of his hairs are infected. So like, you know how sometimes if you shave or something like that, you might get like a little bitty ingrown infected hair or whatever? Well, now all of the hairs on your arm are infected hairs. So let me kind of flip over so you can see this picture a little bit better if you're on the Zoom. So in this picture, you can see the skin of somebody with scurvy. Now, I was telling the other classes, sometimes your skin can look like that because you're like 95 or something. So grandma's skin looks like grandma's skin. It's got bruises, spots, and stuff all over it. So you can have skin that looks like this for like 10 different reasons, but one of them is scurvy. Kind of like my car doesn't start. That doesn't guarantee that it's the battery, but like it could be the battery. So if your skin looks like this, doesn't guarantee it's scurvy, but could be scurvy. So your skin kind of looks like this. We will actually talk about what scurvy is in just a second. Swollen gums. By the way, for my Zoom crew, we got new webcams. So I'm going to install mine today. So this webcam right here will be a lot better and a whole lot less laggy. So that'll be great. I'm excited. Now this guy's in worse shape. This is literally from a textbook, so I trust it, a medical textbook. Those are his gums. His teeth have rotted out, obviously, and his gums are like completely rotten black. And I think this is tattooing along his lip, but I'm not entirely sure. So students will always ask whenever we see certain medical images, like, how did you let it get that bad? Let's say that I've got a cancer in my body that's this big. Well, it's easy to see that I would never notice that. But occasionally you'll hear about somebody that gets like a cancer removed from their body that's like this big. And you're like, how did you let it get that big? Probably denial. But how does he let his mouth get that bad? I don't know, he tattooed his lips. I think this guy's seen things in life. When you start getting tattoos in your lips, have you ever seen where somebody like folds their lips up and it like says something on the inside of their lips? Don't mess with that guy. I think he's done time. I think generally the type of people that tattoo the inside of their gums, they've had a rough life. Maybe not, right? They could be a PhD chemist or something, right? Might say like octane in there or saturated lipids or something, but it's probably not. It's probably a cuss word. So, scurvy. Okay, so how many of y'all have heard? I can remove that image. We'll just go back to Dale. So how many of y'all have heard of scurvy before this class? You might not know what it is, but like you've at least heard of it, heard of scurvy. Does anybody know anything about it? Like what causes it? Like, hey, I don't want that. I don't want to look like Dale, so what do I need? Uh-huh.
Vitamin D.
Close. Vitamin C. Vitamin D deficiency is rickets. Vitamin C is scurvy, but they are both related to connective tissue and bone. So when you lack vitamin C, you get scurvy. You're like, okay, so first of all, what is scurvy? And what does vitamin C have to do with it? Well, whenever you have scurvy, your body makes really crappy collagen. So let me show you a picture of collagen. Collagen, just in case you can't quite hear me like pronounce it very well, collagen is a C-O-L-L-A-G-E-N. So collagen with a C. All right, so collagen. Where have you heard of collagen? Like what body parts do you associate with collagen? Naturally, of course, we can inject like collagen into your lips or whatever, but like where do we typically have collagen? Yeah, hair, skin, connective tissue. Collagen is what makes skin pliable but strong. So if you think about it, you can take your skin and like twist it and it doesn't really tear very easily. Part of that is collagen. I have short hair, but if I had long hair and I like pulled it along the length, like it's pretty strong. If you consider how thin hair is, you know, I mean, Rapunzel, right? So when you pull along the length of hair, it's actually pretty strong. Part of that is because of collagen. Well, collagen is a triple helix. So let me kind of show you what I mean real quick. Get rid of this. Flip on one set of lights. And switch cameras. So here's collagen. Picture a double helix like DNA, but it's not a double, it's a triple. So I've got one strand of black marker, one strand of red marker, and one strand of blue marker. Okay, so if you don't have enough vitamin C, then you have bad collagen. Collagen makes up your skin, connective tissue. It makes up like the lining of your arteries is connective tissue, like lining around your arteries is connective tissue. Heart valves, that's made of connective tissue. So any kind of connective tissue usually has collagen in it. The connective tissue that has the most is like a ligament or a tendon. So if you've ever eaten like a turkey leg or whatever, let's say you go to the fair, you have those giant turkey legs, you know what I'm talking about? Or you're just a kid and you're eating a chicken leg. So I'm not going to draw the whole thing because it starts to look like other things. But here's a chicken leg, and down at the bottom you got like the two little parts that hang out like that, like the bone, that I won't draw. So you eat the chicken part, but then like the handle where you're holding it, there's like that little rubber bandy type thing that hangs down. How many of y'all know what I'm talking about? And you're like, hey, can I eat that? I mean, I've seen dogs eat turds, but so I guess the question is, should I eat that? It depends. It's tendon. It's that animal's Achilles tendon. You can feel your Achilles tendon right back here. You can probably feel some tendons in your wrist, depending on how you hold your fingers. You got tendons on the back of your hand. So muscles in here move up and down, and then tendons pull on your bones. So ligaments and tendons are both made out of a whole lot of collagen. So if you picture tendons and ligaments, that's kind of what collagen is like. So it's It's pliable, it's rubbery, but it's strong. So I always compare it to like braided steel cable. I could like spool it, it's cable, but it's so strong that I can like hold up a bridge with it, right? So strong, but pliable. So that's collagen. Well, it turns out without vitamin C, your collagen melts at less than 80 Fahrenheit. It's somewhere around like 76. It's no longer a solid, it's liquidy. Why is this a problem in your body? Yeah, it's not supposed to melt. And what is your body temperature? Yeah, I mean, everybody's slightly different, but 98.6 is the number we hear the most, right? My normal body temperature is like 97, upper 97s. All of that is well above 80. So my collagen will actually melt. And it won't be a solid fiber anymore, which means my heart valves, my ligaments, my tendons, my ligament that holds my tooth in will basically break down. You know how when you were younger and you were still like losing teeth, you know how you would, see I'm interacting with my Zoom here. You know how you would like have that twisty tooth and it was like hanging on by a thread? That thread was a ligament. And so Dale's teeth are falling out because his ligaments are liquefying. So nothing's holding his teeth in anymore. So you'd have that loose tooth that'd spin around, then eventually you just, I don't know, you just kind of like snap something and your tooth comes out. That snapping something was a ligament. Ligaments and tendons are the same thing. If you attach a bone to a bone, we call it a ligament. If you attach a muscle to a bone, we call it a tendon, but otherwise they're made out of essentially the same stuff. Okay, if I do have vitamin C though, then now I don't melt at 80. Now I melt at 120 plus if I eat vitamin C. So by eating vitamin C, my melting temperature goes up by like 40. If I'm at 120, I'm already dead. You typically die somewhere around 110. So you don't, as long as you have a healthy diet, you will never reach 120 and be alive. So 120 plus. What does vitamin C have to do with any of this? Well, here is how vitamin C works. We spend a little bit more time on vitamins later on in the year, but I'll give you a preview of vitamin C. I've got an enzyme. And somebody, let me see if I can get the Zoom crew. Anybody in the Zoom crew remember? I've got an enzyme, and then an enzyme fits something. Does anybody on Zoom remember what that something was called that happens to like fit an enzyme? Your teacher might have said kind of like a lock and a key or something like that.
Is it a catalyst, or is that what the enzyme does?
The second thing you said was right. A catalyst is anything that speeds up a reaction. So an enzyme is a type of catalyst. So it was the second thing that you said, Isabella. What was the thing that fits an enzyme called? It starts with an S. Anybody that's live, remember? Yeah.
I think it was circulose that you said?
Close. It's SU. It's a substrate. So substrate. So I might have a substrate like this. Does it look like that substrate perfectly fits my enzyme right now? No. So some enzymes have a certain shape, and the substrate fits in there perfectly, like that. Some enzymes, the substrate doesn't fit, and so that's why they need a vitamin. So when I put in vitamin C, now does this fit? It's almost like you need these two puzzle pieces to like fit into this little spot. So for my enzyme, this particular enzyme, to run a chemical reaction, to bind to its substrate, I also need vitamin C. Whenever I take vitamin C and I do this reaction, I use it up. So that's why I need more vitamin C every day. I can't just like take one pill and I'm good forever, because I use up vitamin C. You're like, all right, great. Well, what does this enzyme do? This job of this enzyme that requires vitamin C, what it does, this is pretty clever, is it'll go along my collagen here, and it adds OH groups. OH, OH, OH. All along here. So OH groups, they call hydroxyl. I don't know why chemists changed the name. You might have learned that like an OH is a hydroxide group, but whenever we bond it to something, we call it a hydroxyl. If I have sodium and chlorine, I call it sodium and chlorine, but whenever I bond them together, I call it sodium chloride. They just changed the name a little bit. I don't know why they changed the name, they just do. So a hydroxyl group is when I bond an OH to something. So now, I've got OHs on the blue, I've got OHs on the red string, and I've got OHs on the black string. So, why does that matter? How does adding OHs make this so much stronger? Now instead of melting at 76 or 77, it now melts at 120 something. Why would that up my melting temperature by like 50%? Uh-huh. Yeah, the OHs bond to each other. So think back to water. This is how we want to be able to apply biology. If I understand water chemistry, I'll make those darker. If I understand water chemistry, then I might be able to apply that to this. So here's a water molecule. Here's a water molecule. What happens if a water molecule gets close to another water molecule? So anybody in the live class, what will they do when they're near each other? Somebody said something, but I couldn't quite hear. Yeah, they bond to each other. And what was that bond called? It's always a dotted line. Hydrogen bond. And it was the O's hydrogen bonding with the H's, right? Okay, well, that's a water molecule. If I just sort of go like that, isn't it now an OH? And that's an OH. So couldn't an OH stick to another OH? So what if an OH on the red fiber, maybe the O's hydrogen bond with the H's on the black fiber. And this one, on the black fiber, the H's bond with the O's on the blue one. So they all start sticking to each other. So now, it looks something like this. If I've got a piece of string, like right here, this string will actually kind of fray. So up the top, it sort of frays like that. So this string will come apart. There you go, it's coming apart. Is each string bonded to its neighbor right here, or is it not bonded? It's not bonded, so it's not as strong. But what if I glued each string to its neighbor? Then would this string be stronger? That's what I'm doing. The glue is hydrogen bonds. So I've got an enzyme. It needs vitamin C to work, and it will go in and add OH groups. If I add OH groups to the blue string, the black string, and the red string, and then O's and H's start bonding, then now the blue, the black, and the red are all sticking together, and now my collagen melts at 120 plus, and my teeth don't have to fall out, and I don't die. That's how scurvy works. So, if you want to go into medicine or some sort of biology field, that should be interesting to you. If it's not, you probably don't want to go into biology or a medical field. So, all year long, we kind of keep coming back and just explaining crap like that. We'll learn some stuff like water chemistry, and then water chemistry helps me understand like some sort of disease and vitamin C and stuff like that. So if you're like, oh, that was kind of cool, then good. If your career path is bio, great. But if you're like, this is horrible, I'd rather be in history class, you don't want to major in biology. Okay, does the collagen thing kind of make sense? Hi. Oh, cool. Come on in. Any open seat is yours. They're all clean. If there's not a chair at them, then you can just grab a chair from the back. So, welcome. I'll get you kind of caught up on stuff here just a little bit later. But in the meantime, let me get you a fresh one of these. There you go. Were you in one of my other sections before? Okay. So this is the note stuff we're working on. We're currently on like scurvy stuff. Okay. And at the end of class, I'll kind of like, hey, I haven't been here. You know, I missed the first couple weeks of school, and I'll get you caught up. I have video class and stuff, so we'll get you caught up. Thank you. You're welcome. Welcome to AP Bio. So that's why, like, we can apply all this stuff to something that's kind of cool. Speaking of applying to something that's kind of cool, I'll try to always warn you if a picture is going to be kind of gross, like if it's some sort of surgery picture or something like that. But start off with, it's not gross. So if you flip over to page 2 of your notes, all right, so page 2 of your notes, right in the middle of page, it says lipids. That's what we'll be focusing on. We'll come back and get carbohydrates and stuff later. But right now we're going to be on that chunk in the middle called lipids. And some of these pictures, you don't have to, but if you flip forward a few pages, some of these pictures that I'm putting on the screen are even on there too. Like that picture right there is currently on the screen. So I think you got to go forward like 2 more pages or something like that. Okay, so lipids. Lipids are interesting because lipids are fats, and there's all these good fats, bad fats, saturated fats, unsaturated fats, trans fats, hydrogenated oils. What's good about them, what's bad about them, what seems scientifically accurate or not. We'll basically cover all that today. How does eating unhealthy fats cause heart attacks? We'll kind of cover that. How do we fix heart attacks? How do we unblock arteries? Stuff like that. We'll see pictures of clogged arteries. So today is where we kind of are making more of the transition to where it feels like a biology class and not a chemistry class. But we still have a little bit of chemistry. So this is a triglyceride. Why is it logical to call this a triglyceride? You might not understand the entire name, maybe only part of it. Looks like there's 3 different sections. Yeah, there's these 3 tails. They call them fatty acid tails, 1, 2, 3. That's tri. And then this thing right here is called glycerol. So I've got a glycerol with 1, 2, 3 fatty acid tails, so they call it a triglyceride. You're like, okay, whatever. Have you heard of triglycerides before? You might have a parent or a grandparent, and they take Lipitor, the #1 selling drug of all of human history, to bring down their triglyceride levels. So if grandpa takes any sort of like heart medication, his heart medication, there's a lot of different ones. They might be ACE inhibitors and other stuff. But one of his heart medications is probably Lipitor. He's controlling the amount of fat in his bloodstream, hopefully. So here's another triglyceride. Again, this part right here is all called glycerol, or once we bond it to something, glyceride. And then 1, 2, 3 fatty acid tails. So what's different about these 2 triglycerides? And this one's not like a hard question, like it is what it looks like. Yeah?
The bottom C looks like double bonded on the unsaturated one.
Yeah. I got these 2 saturated fat, or I've got these 2 lipids, these 2 triglycerides. And one of them, all the chains are single bonds. The other one, I've got a double bond. Okay. And we haven't talked about lipids at all in this class yet, right? Like this is new. Okay. Now, depending on your 9th grade teacher, you might have spent a lot of time on lipids. The on-level bio classes didn't really. The pre-AP bio classes should have spent a good amount of time on these. So what we're going to do is almost like water chemistry. We're going to kind of see a few facts and then figure out the rest. Like hopefully it'll just be logical how all this fits together. Okay. Yeah, I'm going to keep it here, so I do have to switch back and forth, but yes, thank you. Oh yes, I do need to switch. Thank you. Appreciate it. Okay, so up here, I'm just going to use this for my glycerol. Then I've got this long chain of carbons. How many bonds does carbon always form? Yeah, 4. Okay, so if I've got a chain of carbons, then I'll have like hydrogens all around, like this. All right. Got bonds. What kind of bonds are these if they're straight lines or solid lines? Covalent. Yeah, covalent bonds are always straight lines. Or solid lines. I guess they can be angled. Okay, so if I'm looking at these, and you'll be seeing the small picture if you're watching over there, but one of these chains is different from this one. Which one is saturated? The top one. Why is it logical that we call this saturated? Like, what does the word saturated mean just in English? Could mean solid. Could mean if these paper towels were saturated with water, can I add any more water? Nope, they're full. So you can think of saturated as being full. So it's full of something. If a shirt is saturated in ink, then you can't add any more ink. Okay, so hold that thought for a second. This one is called saturated. This tail right here, you might not want to draw this tail. I'm getting ready to erase something on it. So I'm going to change it on you. The number of carbons doesn't matter. They name them based off the number. Like octane in gasoline has 8 carbons, octane. Okay, so right now these are both saturated. What happens if I put in a double bond right here? So if I change that single bond and I make it a double, what's wrong with that picture if I leave it as is? What rule did I break? Yeah, this carbon right here now has 5 bonds. Is that okay? No, that's not stable, so it's going to lose a bond. Well, if the double bond stays, then maybe I lose this guy. All right, fine. What about this carbon? Is he currently stable? Nope. So if the double bond stays, he's got to lose somebody, so maybe he loses that. Why do we call this unsaturated? It's not full of hydrogen. So when I'm full of hydrogen, we say I'm saturated with hydrogen, and we say it's a saturated fat. When I start adding in double bonds, the more double bonds I add, the more hydrogens I'm going to lose. So now we call this unsaturated. And if you looked at a food label, let me see if I got anything that might work. Here's some almonds. So if I look at the back of almonds, it'll say I've got 9 grams of mono unsaturated, and I've got 3.5 grams of poly unsaturated. So if you had to guess, what's a mono unsaturated or a poly unsaturated fat? Mono means one, poly means, many. So if I just have a double bond, this would be a mono unsaturated. If I start putting in a second, a third, a fourth, a fifth, whatever, then that's polyunsaturated. Which ones tend to be considered more good for you? Saturated or unsaturated? Unsaturated. Within the category of unsaturated, which one's supposed to be better? Poly or monounsaturated? Poly. Okay. So 1 or 2 more random facts, and then we'll kind of tie all this together to where it actually has meaning. Okay, so saturated fats will look like this. They'll have single tails, all single bonds on the tails. So their shape is basically like a capital E. So if I've got like 6 of them together, there you go. Unsaturated. Their tails look more like this. When I get a double bond, I tend to get kinks. It's not a guarantee. I'm not drawing all the extra hydrogens, I'm just drawing the carbons. But whenever I get double bonds, I increase the likelihood of kinks. Now, you don't have to know this for AP Bio, but just for interest, have you heard of trans fats? Trans fats, like it's illegal to actually cook in trans fats in restaurants in Texas. So McDonald's had to change their fry grease whenever it was 5 years ago, and everybody got pissed because they're like, the fries aren't as good now. They used to cook them in lard, which is just animal fat. They had a mixture of animal fat and whatever else in their special McDonald's fry grease, and they had to change it. And there's actually, I heard a podcast of some guy talking about McDonald's fries. He talked for like 30 minutes. I listened to it on a road trip with my friends just because we were astonished that they were actually talking about this, like all these researchers researching McDonald's fry grease and why they're not as crispy as they used to be. So when you get double bonds, you don't have to know this for AP Bio. There's 2 versions of double bonds. One is called cis and one is called trans. When you get cis double bonds, they make kinks. When you get trans double bonds, they don't. And here in a little bit, we're going to learn that's why trans fats are considered the worst. So there's unsaturated, there's saturated. Okay. When I'm looking at any triglycerides, do they dissolve in water very well? If I take a lump of animal fat, let's say I go to the meat counter at the grocery store, and I grab some bacon, and I cut off all the red part, that's the muscle, and I'm left with like this handful of fat, the white part. If I throw it in water, does it dissolve? Nope. If I cook the bacon grease, and then I try to wash the pan off with just water, doesn't work very well. Waxes don't dissolve in water very well. Why is that? Why don't lipids dissolve in water very well? Anybody on the... Do what?
They're not polar.
They're not polar. Okay, you're exactly right. So lipids are nonpolar. So what do I know about carbon and hydrogen then if the lipids are not polar? This is a really hard question. Lipids are nonpolar. What about water? Was water polar? Yes, okay. So what do I know? What chemical property must be true about carbon and hydrogen then to make them nonpolar? Excellent. Sorry, my throat's kind of scratchy. I don't think I got the COVID or anything, but allergies. Plus, I messed up my vocal cords last week. I think I'm trying to talk too loud through my mask, so blew out like a vocal cord teaching. I was teaching too hard. So maybe that means that they share electrons equally, and that's actually true. If I look at the electronegativity of carbon, it's about 2.4, and hydrogen is 2.1. You don't have to have those numbers memorized. But chemists will say, hey, that's close enough to where they're just sharing electrons equally. The electrons spend equal amounts of time around C's and H's. Meanwhile, water is polar. So if I were to take some water and put it in a beaker, halfway, and I pour some oil on it, will they mix? No. I stir it around. Will they separate back out? Yes. And so what students will say, leaving 9th grade a lot of times, because they're really close to right, is a good student from 9th grade will say well, the water molecules are sticking to each other because they're polar, and then the lipid molecules stick to each other because they're nonpolar, and that's why they separate back out. And that's a really good answer for a 9th grader, but it's not quite right. So what is wrong with that? Let me tell you my answer again. The water molecules are sticking to each other. That's why they are all down there. And the oil molecules all stick to each other. That's why they're up here. And the water's more dense, so the water's on bottom. If oil was more dense, the oil would be on bottom. Which statement is wrong? Statement number 1, water molecules are all sticking to each other. Statement number 2, oil molecules are all sticking to each other. And then that's why they don't mix. Which statement's wrong? Huh? Yeah, number 2. If oil is nonpolar, does it stick to other oil molecules? No, they're just all shunned. So the analogy I give is, let's say that I've got 500 magnets. That represents water. Water's not magnetic. So I put 500 magnets in here, and I put 500 Expo pen caps in here. Still good on audio? Good. And I put 500 Expo pen caps in here, and then I shake it around. Won't all the magnets like stick to each other? Will the pen caps actually stick to each other? No. But water's more dense, so will water be on top or on bottom? Bottom. So the water goes to the bottom, and all the water molecules stick to each other. Where are all the oil molecules? Above or below the water? Above. Are they actually sticking to each other? No, they're just shunned by the water. They're just excluded by the water. So that's why oil and water don't mix. So oil, lipids don't dissolve very well. Apparently that's close enough electronegativity to where they share equally. So saturated fats. Do saturated fats dissolve in water very well? Like bacon? Nope. So we'll just say nonpolar, doesn't dissolve in water. Unsaturated fats, also nonpolar. They don't dissolve in water very well. Unsaturated fats, instead of looking like E's, they look like messed up E's. Kind of more like this. They've got all these kinks. Which ones tend to be more solid at room temperature? Saturated or unsaturated? Like if I knew something was high in fat, like salad dressings tend to be high in fat. I've got one that's runny, like Olive Garden dressing, and I've got one that's more thick, like Thousand Island or Ranch, right? Both of them are pourable, but one of them is like super runny, and one of them, like with Ranch, I could technically probably go like this and maybe not have it dump out. If I did that with Olive Garden dressing, I just dumped out like half of it, didn't I? So what tends to be more solid at room temperature, saturated or unsaturated? Which one tends to be the bad one? Saturated. So saturated tends to be bad. Unsaturated tends to be good or okay. They're both equally high in calories, but this one is more likely to give me a heart attack than this one. So which one is more solid? Saturated is more solid. Okay, now, if I didn't know that, how could I figure that out just based on logic and a grocery store and the meat counter?
Because like the more buddies tend to have like one of my favorite dressings is the vinaigrette dressing, and so they tend to be a lot more runny. And so they're not as thick, meaning they're not as combined.
Right.
They have more double bonds than saturated dressing.
Okay, everything you said is true. So the runny ones have more double bonds. But how would I know? So everything that you said was true. But how would I know? How could I just logic, like if I'm you, if I know that saturated fats tend to be the bad ones, how could I conclude that they're probably more solid? What tends to be worse for you? Animal fat or like olive oil? Bacon, vegetable oil. Which one is worse for you? bacon. I know it's confusing with all the diets where they're like, bacon is good for you, and it's like, no, it's not. Might help you lose weight, but you're still junking up your arteries. So if the bad one is saturated, and I know that like bacon tends to be worse, then that means the saturated one is probably more solid. Unsaturated is probably more liquid. And that is true. So why is Olive Garden dressing more liquidy? It's got more unsaturated fat. Why is ranch thicker and less runny? Because it's high in saturated fats. Why is it logical that unsaturated is more liquidy? Based off of just what you see on the board. Based off of what you see on the board, you're like, oh yeah, saturated should be more solid. And oh yeah, unsaturated should be more liquidy. Do what? The bonds. Why does this look more solid than this? It is related to bonds.
It just like fits together better.
Yeah. In chemistry, his answer was it sticks together better. In chemistry, when I can pack crap together really tight, isn't that a solid? Not as tight as a liquid. Not tight at all as a gas. If I've got like 5 or 6, here, let me get 6. If I got 6 saturated fats and 6 unsaturated fats side by side, who can I pack together better? Saturated or unsaturated? Saturated, because of their chemical shape. Shape is everything. So now let's tie all this in together. Saturated fats tend to be solid. Why? Well, they have straight fatty acid tails. Why? Because all their bonds are single bonds. Unsaturated fats tend to be more liquidy. Why? Well, they have kinks in their tails. Why? They tend to have more double bonds. Okay, so now, they're both high in calories. So why is this one bad and this one good? This is the important part from like a health standpoint. Most people don't realize that your body doesn't chemically break down fat before it squirts it into your bloodstream. You only physically break it down. So protein. Let's say that I eat some almonds and there's protein in here. My body will take the protein. Let's say this is my protein. Think back to 9th grade. What were the building blocks of proteins? Amino acids, yeah. So my body, by the time it goes through my stomach and into my intestines, I actually break it down into individual amino acids. And then I squirt those amino acids into my bloodstream. They go wherever they go in my body. And I'm good to go. So I chemically break them down. Fats, I physically break them down. So think back to chemical change versus physical change from elementary school. If I've got a glob of fat and I physically break it down, isn't it still just a whole bunch of teeny tiny globs of fat now? Like a physical change, if I had a boulder and I just hammer the crap out of it, now it's just a whole bunch of teeny tiny boulders. We call it sand, but like it's a whole bunch of teeny tiny boulders. Okay, so I eat some fat. Let's say it's like bacon grease. Does it dissolve in water very well? No. What's my blood made out of mostly? What are you made out of mostly? Water. So if I'm about 2/3 water, I eat some fat. I just break it down into teeny tiny little bitty globs. And then I squirt it into my bloodstream. My bloodstream is mostly water, so does that fat dissolve in water? No. I eat some olive oil. I squirt that into my bloodstream. Does it dissolve very well in my blood? No. Which one's going to clog my arteries? Saturated or unsaturated? Saturated. Why? Because it's solid. And I have solid crap floating around in my bloodstream. If it's olive oil, it doesn't clog my pipes. If I had a thing of olive oil, I am aware this is soap. It's more for my 9th grade students. They're like, you know that's soap, Mr. Cotton, and I'm just like, I can't punch you in the face right now, but like if I, so anyway. So let's say this was olive oil, and I turn on the water. I've got a faucet over here with a drain. And I turn on the water and I dump olive oil down there. Is it likely to clog the drain? No, it doesn't dissolve in water, but it's also pretty slippery. It doesn't stick to the pipes. What if I cook bacon? Now I'm done with the bacon and I pour the bacon grease down the drain. Does that clog the pipes? Yes. Aren't those pipes kind of like my arteries? And isn't that water kind of like my blood? So whenever I eat fat, my body just physically breaks it down into teeny tiny little bitty globs of oil or chunks of fat and squirts it into my bloodstream. If I had pretend this was like an Ozarka bottle, and I filled it half with water and half with olive oil, shook it around, and then dumped it, wouldn't most of the oil come out? Would it be clogging this a whole lot? Not a lot. Some of it, it'd leave like a little film behind. Now, half with water, half with bacon grease. I shake it around. I dump it. Isn't like half the bacon grease still stuck to the side of this? Yes. So that's what happens in my arteries. When I eat saturated fats, they're nonpolar, so they don't dissolve in my blood when they squirt in there, and they're solid. So it starts clogging my arteries. Okay, now, let's say I've got an artery this big around. I don't. Let's say that I do. The biggest artery in your body should be, if you go index finger to that joint in your thumb, that's about how big your aorta is. So if you're a 7-foot tall person, you probably have hands that are a lot bigger, and you'd have an aorta that's a lot bigger. If you're 5 feet tall, you'd have smaller hands, and so your aorta is smaller for your smaller body. So, but let's say that I've got an artery that big, and I'm supposed to pump blood through it. Now, I clog it with fat, and it's only that big. What happens to the pressure inside of that artery? It increases. That's why we measure your blood pressure. We measure your blood pressure because we're trying to take a guess at what your arteries look like inside. When your blood pressure is high, it's like, ooh. Your blood pressure is either high because you like ran over here, because then your heart's pumping harder, right? No duh, that's exercise. That's the whole point. So my blood pressure is high when I'm exercising. It might be high like if I'm at the doctor and I'm just afraid of doctors, I'm nervous, then my heart rate might be up, so my blood pressure might be up. But it could be because my arteries are clogged. So that's why we test your blood pressure. Is, hey, maybe your arteries are clogged and that's why your blood pressure is high. Okay, so now let's apply this to disgusting stuff. Well, some stuff looks pretty good, actually. So let me switch cameras here. Okay, 10, 11. Okay, cool. So this is a Baconator from Wendy's. It says it has 6 strips of bacon, 2 slices of cheese. Cheese is high in fat. Would you generally say that cheese is something you pour at room temperature, or is it more solid? It's more solid. So what kind of fat is it higher in? Saturated, right? Just like the salad dressing. Which one's worse for you, the ranch or the Olive Garden? Probably the ranch because it's thicker. Now, Olive Garden might have twice the salt, so it might be bad for you in that sense. But from an artery clogging standpoint, the thicker stuff tends to have more saturated fat. 2 quarter-pound beef patties. It says it's one mean and delicious burger, and that looks like it's mayonnaise on it too. Isn't mayonnaise pretty thick? And it's fatty, so that's also saturated fat. I always think mayonnaise is disgusting. Yeah, I hate mayonnaise. That's a Baconator in real life. Now, many of y'all have probably eaten at Sonic. So you go to Sonic, they wrap your burger up in that special, it's like paper on the inside, but foil on the outside kind of paper like this. You can see the grease, the fat dripping off of it. How many of y'all, you get the Sonic bag, and after like 5 minutes, there's literally like oil leaking through the bag? Or you go to Little Caesars, there's freaking cardboard on there, and there's grease that's leached all the way through the cardboard at the bottom of the thing. Like, that's how much fat is in there, which is disgusting. Like the burger grease got past the paper, past the foil, and like it's now leaving the bag. I don't know. It's kind of gross. It's a quad stacker. At Burger King, they kind of have a little bit more of a sense of humor. So you can go double meat, that's bold. Triple meat is brave, and quadruple meat is ballsy. I appreciate the humor at the King. That's 4 quarter-pound patties, by the way. The standard, if you're in the ground beef section at a grocery store, that standard size that they already have pre-wrapped, that's a pound. So that's that much meat. Plus the cheese, plus the bacon. That is ballsy. I agree. I agree with you, King. So here's a quad stacker. They went lighter on the cheese, trying to be heart healthy. It is sitting on a plate of French fries, though, it appears. Vegetables. Some mayonnaise on the top. This is a Baconator on top of a quad stacker. I don't know if any of y'all ever been to K-pop and seen some of the burgers that they have pictures of at that place. Their burgers are awesome, by the way, but they'll kill you. So who takes a picture of this? Somebody at supersizemeals.com. Supersizemeal.com is a website where people just publish pictures of insane fast food combos that they eat. So it'll be like, hey, a quad stacker on top of a Baconator. And you're like, oh my gosh. So here's an artery. Oh, thank you. I must have hit the thing. Let me go back to the Zoom part. See if I can fix it. This might have been what happened the other day. There you go. Is that better? Thank you. Click the wrong button there for a second. Okay, so if I go back over here and look at this artery, this is like an artery, like you're looking down the barrel of an artery. So here's my artery, a big long tube. And if I kind of turn it this way and cut through it, you're like looking down the barrel of an artery. So this is a clean artery. The blood flows all through the middle right there. That's fine. So, but then that person on supersized meals, they ate their quad stacker on top of a Baconator, so their artery looks like that. All of that is fat. So now the blood just flows through there. So what is this person's blood pressure like? Crazy high. Now, let's say that I've got an artery that feeds like my right arm, and it gets 50% clogged. Does my arm suddenly need less blood? No, it still needs just as much oxygen and food, but now my heart has to pump a whole lot harder to push the same amount of blood through a smaller hole. So imagine I've got fire hose type of water flow, and I now have to shove it through a garden hose. Whatever engine is doing the pumping, isn't that engine going to be working really hard? Yes, that's why eating garbage causes a heart attack. Because you're clogging your arteries, and now your heart has to pump harder just to get its job done. If the pressure's too high, couldn't my garden hose like swell and maybe even burst? What's that called when an artery swells? It starts with an A. It's a really weird word. An aneurysm. And then if it bursts, we call it a burst aneurysm. So if an aneurysm is feeding this part of my brain that controls the left side of my body, and I have an aneurysm and it bursts, and now that part of my brain dies, this side of my body is paralyzed. Whenever brain cells die, we call it a stroke. So maybe somebody has a stroke because they had an aneurysm that burst, and if that burst aneurysm, that blood was supposed to feed this part of their brain, then they lose that function. If it fed this other part of their brain, speech is here and here, then all of a sudden grandma can't speak anymore because it damaged her Broca's area. Broca's area is where you speak. Does the brain fix itself? Nope, brain cells and spinal cells suck at fixing themselves. So it's permanent damage. I'll show you at some point. There's this like terrible traffic circle right at the base of your brain called the circle of Willis, where 5 converge onto literally a circle and then branch back out. And when it hits that circle, that's where aneurysms happen. It's just, our brain vasculature is just poorly engineered. But if you keep them clean, you'll probably be okay. You start clogging them with fat and they swell and burst. So this person, I mean, this is a dumb statement at first, but I say it every year. Before this person died, they were alive. With that, Can you imagine what their heart was doing? Like 5 minutes before this guy died from a heart attack, he was living and his heart was pumping hard enough to shove blood through that little bitty hole. All that is fat. It's crazy. This is blood plasma. So let's say we usually have a fall and a spring blood drive. I don't know with COVID if that's going to happen or if maybe we'll have even more. But with the blood drive, you might give a bag of blood. Well, what they can do is they can take the blood and they can like pull out all the cells, all the solid stuff like red blood cells and things like that, and just leave behind the liquid. The liquid they leave behind is called plasma. Do you see a difference between these two bags of plasma? Do you see that this one has chunks of white crap floating in it? What is that? It looks cloudy. That's fat. Just like if I have water and I add baking grease and I shake it up, now isn't the water all cloudy with hunks of white crap floating in it? That's that person's plasma. That is a chunk of fat right there. When one glob of fat touches another, don't they stick together? You can see it in the person's plasma. If I was a phlebotomist, like if I worked at Carter Blood Bank or whatever, when I pull your blood, I can be like, holy crap, what did you eat? And you're like, what? And it's like your blood is cloudy. Why? I can see the fat floating in your blood. It's amazing. That's clean. Obviously, before they give this to somebody, they're going to clean it up too. But here's another clogged artery. This one always looks like an angry person with a large nose to me, like eyeball, and a large nose. This is the one I think you were mentioning earlier. This one I call foreshadowing. It's got a fried donut, a corn dog, and a clogged artery. This one is as real life as you can get. Let's say that there's a guy, and I'm a pathologist. I'm a medical examiner. So when somebody dies, I sometimes have to determine the cause of death. So I'll do an autopsy. So I think this guy died from a heart attack. Why? He's American, and I'm looking at him. He looks like he would die from a heart attack. So I cut him open, and I start pushing around on his heart. So there's a few like major arteries on your heart that tend to get clogged, that when they get clogged, you die. So I kind of find those arteries, and I push around, and all of a sudden I feel like a little lump in there. So then I can go in and like cut through that artery and see like, hey, is it blocked? And give you an estimate like, yeah, it's like 50% blocked or 40% blocked or 90% blocked, whatever. So this is literally a picture. If you take a person's coronary artery, so here's the artery, you cut it, no stain, nothing. You just pull out your phone and like take a picture as is. So this is like, here's an artery, snap. The wall of the artery is here. All of this is fat. Can you see that it looks gristly? That's because it's gristly. Can you see that it looks just like a hunk of fat you cut off a steak? That's because that's what that is. This fat is from steak. That looks like fat from steak. It's fat from steak. Hence the similarities. That's amazing. This one just for fun. On the left is a beefy 5-layer burrito, and on the right is a clogged artery. And they look like each other because this is from totallylooks.like.com. You're like, what is totallylooks.like.com? It's a website. It's all about stuff that totally looks like other stuff. Next picture is going to be rough, so you don't have to look if you don't want. So this is an artery, and instead of looking at a cross-section, we've been looking at cross-sections, which is like you're looking down the barrel of an artery this way. Now we're going to look sideways. So here's an artery like this. This is a tube, an artery, and we're going to cut it along the length, almost like you might cut down the length of a hot dog and look in the middle of it. Here's how wide that artery is supposed to be. This part is clean. Then I see some yellowish fat crap right here, and then I see a blood clot, a thrombosis. So this part got clogged. Here's how wide the artery is supposed to be. Here's how wide it is now. That's an aneurysm. So my first question is, which way was the blood flowing? Was the blood flowing from left to right? Or was the blood flowing right to left? Right to left. Because if it's flowing from right to left and all of a sudden you hit a traffic jam, isn't all the pressure right before the traffic jam? If 10 lanes of traffic narrow down into 2 because of a wreck, isn't all the pressure right before the narrow down? So this expanded and expanded and expanded, and I'm not sure if it ruptured, but again, I didn't get out like a ruler and measure it, but that looks like it's, I don't know, 5 times maybe? Yeah, 4, 5, 6 times in diameter. It's a big old aneurysm. Next picture is a little bit rougher. You don't have to look. This is a surgery where they have a close-up of an aneurysm. So let me kind of orient you to the picture. We're super zoomed in. Fingers up here would probably be about this wide. And this right here is the artery. It is now ballooned to be an aneurysm this big. And then this branch off of that artery is also an aneurysm. So it's supposed to be, it's ballooned out to be that big. So if aneurysms are small, we can sometimes go and kind of scrape them out, maybe inflate a balloon in there to kind of smash all the fat to the side and like leave a stent, like a little mesh kind of holder opener type of thing. But when they're too big, we just have to cut it out. So you have seizures sometimes? You okay? Oh, stay down for a second. You all right?
Yeah, I'm good.
Okay. Have you ever had a seizure before?
No.
Okay. Is it all the stuff on the screen?
Maybe, I don't know.
Okay. It's been a rough year for these pictures. Had another student that had to, maybe I need to reevaluate some of my pictures. So, I'll switch pictures. Nope, nope, nope. Hang on. Go with this one. No, let's not go with that one. Hang on. We'll go with this one. Cholesterol. So, if I'm looking at cholesterol, cholesterol is also nonpolar, so it can also clog my arteries. Do any of y'all have a parent or a grandparent or somebody that you know is taking like Lipitor or anything like that? Or do you know? Do you know if like grandpa takes heart medication or anything like that? Okay, so cholesterol can also clog your arteries. But have you ever heard of steroids, like anabolic steroids, for example? Anything that comes from cholesterol is called a steroid hormone. So cholesterol is bad because it can clog your arteries, but it's also good because that's how we get testosterone and estrogen and progesterone, aldosterone. So what we'll eventually see when we look at cholesterol a little bit more closely is cholesterol has this certain shape, and then cholesterol-based hormones have that same basic shape as well. Now, after all this stuff about eating unhealthy or clogging your arteries, you're like, Mr. Cotton, we'll end with this. You're like, I would like some good news. I love cheeseburgers. Are my arteries going to always be clogged? Not necessarily. So what happens is you have these proteins. You might have heard of HDLs or LDLs before. But you constantly have these proteins that are fighting to either clean fat out of your arteries and store it in your liver, or take it out of your body and dump it into your bloodstream. So the problem is, if I eat too much fat in a meal, the guys that are taking the fat out of my bloodstream and storing it somewhere, they can't keep up. So if I eat some fat, but not a ton, my body can actually clean it out of my arteries and feed my cells with it. But if I'm eating this much fat, and I can only clear out this much by my next meal, and my next meal has this much fat in it, then I always have fat circulating around in my arteries. So it's possible to have arteries that are 50% clogged, start eating better and start exercising, and then now they're 40% clogged, or 30% clogged, or 20% clogged. So some of clogging your arteries is reversible. If I exercise, then my body pulls fat out of my bloodstream for energy so that I can exercise. That's why exercising helps. Have you ever heard that exercising, especially if you have a really stressful job, that you should exercise so you don't have a heart attack and die? One of the reasons is when I'm stressed, I'm dumping fat into my bloodstream. If I exercise, my body takes it out to feed my muscles. So as long as I'm exercising, I could technically get away with eating a little bit more unhealthy, probably. So, all right, we'll stop there for today because I'm going to check and see if we have some TCTV for us. Okay, give me 1 second. All right, real quick for the home crew. Let me switch cameras. All right, you guys doing okay on the home front? Cool. I'm going to put TCTV on, but I can't have, long story short, my microphone port and my speaker port are the same one. So I can't put it on in a way where you guys can hear it. If you go to the Talon, of course you can watch it. But basically, since you won't be able to hear it here, then you guys are done. So if you have a question, go ahead and fire away and I can try to help you out. But otherwise, I'll dismiss you guys. You good? All right. Well, thanks, y'all. I'll see you in a couple of days. Let's see. Yonder. There we go.